Okay, hello everyone. Let's start our new session. Today, the first speaker is Veronica Danesi. She's currently a postdoctoral researcher in mathematics at University Roma Tor Vergata in Italy. She obtained her PhD in mathematical science in 2021. During her PhD, as well, her first postdoctoral position, her research focused primarily on Hamiltonian system, camp theory, and application to celestial mechanics. Her current research interests are centered on inverse problem and partial differential equation. Alongside her academic career, she recently completed a second-level master's degree in space science and technology, which gave her the opportunity to collaborate with Thales Alenia Space Italy in Italy and the Italian Space Agency on projects related to optimal control, orbital dynamics, and planetary defense. So today she will give a talk entitled Reconstruction of Degeneracy Region and Power for Parabolic Equation and Systems. So thank you very much, Veronica, for accepting to give a talk, and you can start.
Thank you, Anna, for your introduction, and I would also like to thank the organizers for their kind invitation. In this talk, I will present some results about the inverse problem of recovering the strongly degenerate region in power for parabolic equation systems. And this is a work in collaboration with Pier Marco Cannarsa and Anna. First of all, what are the motivations for our work? Degenerate parabolic equations have attracted increasing attention both for their theoretical and practical application in several fields like climatology, financial mathematics, and also population dynamics. For our problem, we will consider the heat diffusion in a body with a conductivity failure. The coefficient K represents the thermal conductivity, which is related to the structure of the material, to the density and other factors, and it can degenerate. And its degeneracy indicates the ability to resist heat transfer. So what is our goal? We want to solve the inverse problem of determining this coefficient K from suitable additional observations of the solution. The starting point of our investigation is the work by Cannarsa, Dubova, and Yamamoto in 2024, where they studied a one-dimensional scalar model where they consider a linear decay rate for the degenerate coefficient. And they want to reconstruct an interior degeneracy point for this kind of models, starting from additional measurements of the solution. But what is our aim? We want to solve the same kind of identification problems, but not only in the scalar case, but also for degenerate systems. And we want to consider a more general setting for the strongly degenerate problem. So we consider also theta between 1 and 2. And moreover, we want also to try to solve the inverse problem of recovering the degeneracy power. To perform this generalization, first of all, we introduce this complex parabolic equation with theta between 1 and 2, and where we have also added this zero-order term with a constant complex coefficient C, which is equal to alpha plus beta. And we want to solve the inverse problem of recovering an interior degeneracy point starting from an additional observation. But we are considering Dirichlet boundary conditions, and we want to reconstruct an interior degeneracy point. So the natural additional observation for this problem is the normal derivative at the boundary. Starting from this complex formulation, we can also rewrite our equation as a coupled real system of this kind. And we are in a degenerate setting. So the first step is to introduce suitable energy spaces, which of course depend on the degeneracy. So we introduce the space L2, and we define our operator bold A in this way, where capital A is the real diffusion operator, and where U and V are real value functions. First of all, we introduce the space of function h1 theta, which is the Sobolev space where we take into account the Dirichlet boundary condition, and where the first derivative is weighted depending on the degeneracy point and the degeneracy power. Then we can define the domain of our operator, which is the space h2 theta, which is the space of functions which belong to the space h1 theta, and for which also this second derivative is weighted depending on the degeneracy point and the degeneracy power. What about the properties of our operator? It is a dissipative and self-adjoint operator with a dense domain, and it is also the infinitesimal generator of a semigroup of contraction, which is also analytic. And we have that also this map is an analytic map for positive time. And our problem can be written in this abstract form, where of course we have to take into account also the presence of the zero order term with the constant coefficient C. And the solution given by this formula is the solution of the problem in the sense of semigroup theory. If we then introduce also the definition of a strict solution, we can say that if our initial datum belongs to the space h1 theta, we can say that the solution in the sense of the semigroup theory is also the unique strict solution of our problem. So we have the well-posedness of the direct problem. What about the well-posedness of the inverse problem? The existence of the solution relies on the well-posedness of the PD problem. So the three main questions for our inverse problem are the uniqueness, the stability, and the reconstruction. As regards the stability, can you see the full screen?
No, it's okay.
Sorry, I don't know.
Don't worry. Oh.
Okay.
Okay, perfect.
Okay, the three main questions for our inverse problem are the uniqueness, the stability, and the numerical reconstruction. If we have two solutions which correspond to two different degeneracy points, and we have two observations which are equal, so then the question is, can we have that also the two degeneracy points are equal? As regards to the stability, we want to have a Lipschitz stability property. So the question is, can we estimate the distance between the two degeneracy points in terms of the distance between the two observations? And the last question is how can we reconstruct numerically our unknown, starting, of course, from the observation. So, okay, first of all, let us observe that we are considering a strongly degenerate problem. And in order to have a function W which belongs to the right weighted energy space, we need that this function satisfies this weighted Neumann condition at the degeneracy point A. So this means that there is no transmission of information from one side of the degeneracy to the other. And this results in the fact that our strongly degenerate problem can be decoupled into two completely distinct subproblems of boundary degeneracy in the left interval 0A and in the right interval A1. So now let us focus on the right subproblem in the interval A1, where we automatically have this weighted Neumann condition. So our method is based on the spectral analysis for the diffusion operator. We want to solve this eigenvalue problem in the right interval A1. It can be solved by using Bessel functions of the first kind and of order in theta, which is defined in this way. And solving this problem, we obtain this expression for the eigenvalues, which depend on the degeneracy point and on the degeneracy power, and of course also on the zeros of the Bessel functions. While the eigenfunctions depend on the degeneracy point, the degeneracy power, and the Bessel functions. So now we have an explicit form for the solution and also for the normal derivative. The explicit form for the normal derivative can be written in this way, where, of course, we have to take into account also the presence of the zero-order term with the constant coefficient c, which is equal to alpha plus I beta. So we have this exponential term for alpha and this rotation matrix for beta. While this vector is the vector which takes into account also the scalar product with the initial data. So now we have the explicit expression of the normal derivative. We want to solve our inverse problem in the right subinterval A1. In particular, we want to reconstruct the value of the degeneracy point, and we start considering a one-point measurement of the normal derivative. So we consider a measurement of the normal derivative for a fixed time t star, and our first goal is to obtain a Lipschitz stability estimate for our problem. So in order to obtain this goal, we reformulate our inverse problem in this way. So now the question is, are there initial data such that for some time and for all the value A in compact intervals, the absolute value of the derivative with respect to A of the normal derivative is greater than 0? If we have such a property would ensure the injectivity of the map which associates A to the normal derivative, and also a Lipschitz stability estimate of this kind. So now we can state our Lipschitz stability result with a one-point measurement. We take a degeneracy power theta between 1 and 2. We consider initial data of this kind, and we also assume this condition on the initial data, which is a simplified condition. We can also consider a more general condition which takes into account the Fourier coefficient, the first Fourier coefficient. Then we consider two different degeneracy point A1 and A2 and their corresponding solutions. And then we can say that there exists a time t0 and also a constant c, such that this Lipschitz stability estimate holds for all the value of A1 and A2 in compact intervals of this kind, and also for all t in compact intervals all greater than t0, depending on the value of the first eigenvalue and of the parameter alpha. This distinction simply means that the zero-order term, in particular the real coefficient of the zero-order term, gives simply a translation of the first eigenvalue. What is the idea of the proof for this result? As I said before, we want to check that this absolute value is greater than 0 for t large enough. And in particular, we want to exploit the explicit expressions for the solution and for the normal derivative in terms of Bessel functions. And we have to perform several estimates, neglecting also suitable terms for t large enough. So now let us see an example of initial conditions for which we can have this Lipschitz stability estimate uniformly on compact intervals and for t large enough. For instance, if we fix a time that is not sufficiently large, for instance, t equal to 0.7, we can see that there is a point A for which the absolute value of the derivative with respect to A of the normal derivative is equal to 0. So we cannot have the desired condition uniformly on compact intervals. But if we fix a time which is large enough, for instance, t equal to 1.4, we can see that we always have the desired condition as long as we stay away from this region. But this is somehow natural because when A goes to 1, the normal derivative goes to 0. So this simply means that we have to stay away from the measurement region. So we can fix several compact intervals with different endpoints, and we have the desired condition as long as we stay away from A equal to 1, which is our measurement region. So now we have a Lipschitz stability result and also a uniqueness result with a 1-point measurement. Now we want to consider two more general inverse problems. In the first problem, we want to consider as unknowns not only the degeneracy point A, but also the initial data. And we want to solve these inverse problems in the right subinterval A1, considering a measurement of the normal derivative in a time interval T1, T2. While in the second problem, we want to reconstruct the degeneracy point A, the initial data, but also the zero-order, the coefficient C of the zero-order term. And in this case, we want to consider measurements of the normal derivative, not only at one side of the boundary, but at the two sides of the boundary and in the time interval T1, T2. So we have two different kind of inverse problems with different unknowns and also different observation, which are distributed measurement over a time interval of the normal derivative on one side of the domain or two sides of the domain. Okay, let's start with the first problem. So now the unknowns are the degeneracy point and the initial data. We are working in the right subinterval A1, and we are considering a one-side distributed measurement of the normal derivative. So we consider two different degeneracy points and their associated solution, which correspond to different initial data. If we assume this sufficient condition on the initial data, that can be generalized as before. If we have that the two normal derivatives are equal in the time interval T1, T2, then we have the uniqueness of the degeneracy point and also of the initial data in the right subinterval A1. What is the idea of the proof? Of course, as before, we want to rely on the explicit expression of the normal derivative, but in this case, we have also to exploit the analyticity in time. But the key ingredient of the proof is the monotonicity of the first eigenvalue with respect to the parameter under reconstruction, which in this case is the degeneracy point A. but we have the explicit expression of the first eigenvalue, and we can see that we have a monotonicity property, so we are able to obtain a uniqueness result for this inverse problem. Okay. As regards the second problem, now the unknowns are the degeneracy point, the initial data, and also the coefficient of the zero-order term. In this case, we are working both in the left subinterval and in the right subinterval, and we are considering two-side distributed measurements of the normal derivative, distributed in time. And if we consider two degeneracy points and their associated solution, which correspond in this case to different initial data, but also different coefficients of the zero-order term, then if we have this sufficient condition, then if the two normal derivatives at two sides of the boundary are equal, then we can have the uniqueness of the degeneracy points, the uniqueness of the coefficients of the zero-order terms, and also of the initial data, but in this case in the whole interval 0, 1, and not only in the right subinterval V1. So now, to better highlight the difference between these two uniqueness results, I want to show you some numerical simulation for real coupled system. Where we consider in particular this system in the whole interval 0, 1, and we want to reconstruct the degeneracy point and the initial data. In two cases, with distributed two-side measurements of the normal derivative and with only a distributed one-side measurement of the normal derivative. So let's start with the case with distributed two-side measurements. In this case, we consider as given the two distributed measurements and only for simplicity the initial datum V0. And we want to solve these inverse problems. We want to reconstruct the degeneracy point A and a piecewise constant initial data, which is defined with different constants on the left subinterval 0A and on the right subinterval A1. And in order to solve this inverse problem, we reformulate it as an optimization problem in this way. So now we want to find A and the initial datum U0 such that that minimize this functional, which is defined in this way, where we take into account the two distributed two-side measurements of the normal derivative. So, okay, to solve this problem, we use the MATLAB optimization toolbox, in particular the F-Mincon function with a gradient-based algorithm. For this simulation, we fixed our parameter in this way, and we start from these initial guesses for our unknowns, while these are the values, the desired values for the unknowns. If we look at the plot of the evolution of the cost, we can see that it becomes very small. And if we look at the plot of the iterations in the computation of the left and the right initial datum U0, we can see that we are able to obtain the two desired value 1 and 2. So we can say that with a two-side distributed measurement of the normal derivative, we are able to solve the inverse problem in the whole interval 0, 1. What about the case with a distributed one-side measurement? In this case, we consider as given, of course, the distributed measurement, and as before, only for simplicity, also the initial datum P0. We want to reconstruct the degeneracy point, and also in this case, a piecewise constant initial data. We reformulate also in this case our problem as an optimization problem with a different, of course, with a different function. And we perform our simulation with this parameter, starting from these initial guesses, and these are the desired values for our unknowns. But now if we look at the plot of the evolution of the cost, we can see that it doesn't become small. Here we have a 45. And if you look at the plot of the iterations in the computation of U01 and U02, we can see that we are not able to recover the two desired values 1 and 2. But we can also observe that we have a better approximation for the right initial datum in the right subinterval A1. So with a one-side distributed measurement of the normal derivative, we cannot solve the inverse problem in the whole interval 0, 1, but these results suggest to try to solve this kind of inverse problem in the right subinterval A1, as we expect from the theoretical uniqueness results. So if we now fix also the left initial datum in the left subinterval 0a, and we fix the other parameter in this way, now if we try to solve the inverse problem of recovering the degeneracy point and the initial datum only in the right subinterval A1, then we can see that the cost function becomes very small and that we are able to recover the desired value for the initial datum in the right subinterval A1. So with a one-side distributed measurement, in this case at x equal to 1, we are able to solve the inverse problem in the right subinterval A1. Of course, with a one-side distributed measurement at x equal to 0, we are able to solve the inverse problem also in the left subinterval 0a. So, okay, now I want also to consider a different kind of inverse problem. Now I want to consider as unknowns the degeneracy power and the initial data. So now A is given, so the degeneracy point is fixed, and we want to reconstruct in particular the degeneracy power starting from a distributed one-side measurement of the normal derivative. So in this case, we consider two different degeneracy power with their associated solutions, which correspond to different initial data. If we assume this as before, this sufficient condition, then we have that if the two normal derivatives are equal on this time interval, then we can obtain the uniqueness of the degeneracy power and also of the initial data, only, of course, in the derived subinterval A1. Okay, what about the proof? As before, we exploit the explicit expression of the normal derivative and also the analyticity in time. But as before, the key point of the proof is the monotonicity of the first eigenvalue. But in this case, with respect to the parameter theta, which is the parameter under reconstruction. And in this case, the monotonicity property is not so immediate from the explicit expression of the first eigenvalue. It is much more difficult to obtain it in a direct way. So we have to introduce a more abstract framework. In particular, we want to exploit a compactness property because we are considering the case theta less than 2. So we have this compact injection between the space H1 theta into L2. And of course, we have the validity of the Spectral theorem, but in particular, we have the variational formulation of the first eigenvalue. And we want to exploit it in order to prove this monotonicity property for the first eigenvalue. So we are able to prove this monotonicity property with this abstract framework, and in the end, we are able to prove the uniqueness result also for this kind of inverse problem. Okay, as before, we are able also to perform the numerical reconstruction of our unknowns. In this case, we consider as given the distributed measurement, of course, and also the initial datum V0 only for simplicity. And then we fix also the degeneracy point and the initial datum in the left subinterval 0a, because we want to solve our inverse problem in the right subinterval a1. So we want to reconstruct theta and piecewise constant initial data, in particular the right constant u02. As before, we have once again an optimization problem. We want to minimize this functional. And we can see that if we fix this value for our parameters, starting from these initial guesses, we try to reconstruct these desired values, and we obtain the convergence of our algorithm. So this is the value of the final cost. And if we look at the two plots for the degeneracy power and also the right initial data u02, we can see that we are able to recover the two desired values of 1.5 and 2. So with a one-side distributed measurement, we are able to solve also this kind of inverse problem in the right subinterval A1. Okay, to conclude now, let's move to the multidimensional case. In this case, we consider this degenerate parabolic equation in the d-dimensional annulus, where the degenerate coefficient is of this kind, with a degeneracy power between 1 and 2. So we are once again in a strongly degenerate setting. The degeneracy occurs only on the interior boundary, where we automatically have the weighted Neumann condition, while we prescribe the Dirichlet boundary condition on the outer boundary. Also, in this case, we are able to introduce an abstract framework. So we have to do a lot of work in order to introduce the right functional setting. So we introduce the weighted energy spaces. We prove that we have a diffusion operator which is maximal dissipative, self-adjoint, and it has also a compact resolvent. So we can, we have, as before, a variational, of course, the validity of the spectral theorem, but also the variational formulation of the first eigenvalue. And we are able also in this multidimensional setting to prove the monotonicity of the first eigenvalue with respect to the degeneracy power theta. And this is the key ingredient in order to obtain a uniqueness result for the inverse problem of recovering the degeneracy power and also the initial data. So we want to solve this kind of inverse problem where now the unknowns are the degeneracy power and the initial data, but now we have a d-dimensional object. So in dimension 1, the distributed measurement of the normal derivative is enough in order to recover both the degeneracy power and also the initial datum. But now we are in a d-dimensional setting, so we have a d-dimensional object, and we have to distinguish between two levels of observations. So we have a global observation, which is the integrated flux on the external boundary. And this is enough in order, this is sufficient in order to recover the degeneracy power. But if we want to recover also the d-dimensional initial data, we need a richer observation, which is the pointwise flux on the external boundary. So we consider also a second observation, and now we are able to obtain a result also for the initial data. Of course, also the uniqueness theorem reflects this distinction between the two observations. So if we consider two degeneracy power θ1 and θ2 and their associated solutions, which correspond to different initial data, if we assume this condition that can, of course, can be generalized with a condition on the first Fourier coefficient, then we have that if the two integrated flux, which correspond to two different initial data, are equal on the time interval T1, T2, then we obtain the uniqueness of the degeneracy power. Once theta is identified, if also the pointwise fluxes are equal here on the external boundary and for the time interval T1, T2, then we are able to obtain the uniqueness also of the d-dimensional initial data. So what about the numerical reconstruction? Also in this case, we have to distinguish between these two observations. So we have two possible numerical reconstruction. We can reconstruct the degeneracy power from the integrated flux. And then if we consider also a pointwise flux, we can reconstruct the initial data starting from this second observation. The multidimensional case is still a work in progress. So for now, we have a numerical test only for the degeneracy power reconstruction. And at this stage, we are considering a simplified setting compared to the theoretical uniqueness result. Indeed, in the theorem, we were able to obtain the uniqueness of the initial the degeneracy power starting from the integrated flux, also when the initial datum is not known. But for this numerical reconstruction, at the moment, we are assuming a simplified setting. So the initial datum is fixed, is known, and we try to reconstruct the degeneracy power with any known initial datum. So for these inverse problems, we want to find the degeneracy power theta, starting from this kind of observation. So starting from the integrated flux, we reformulate once again our problem as an optimization problem, where we want to minimize this functional. And if we fix, for instance, this parameter and we consider this initial datum, we can see that starting from this initial guess, we are able to recover the desired value for our known. So we are able to recover the degeneracy power, and we can see from the plot of the evolution of the cost that the cost functional becomes very small. So with a distributed measurement of the integrated flux, we are able to solve the inverse problem for the degeneracy power also in the multidimensional case. So to conclude, we have achieved several results for several identification problems for strongly degenerate coupled systems in the one-dimensional case and for a strongly degenerate equation in the multidimensional case, which is still a work in progress. But as regards also open questions and future developments, we can see that one goal could be to try to solve this kind of inverse problems also with other technique in order to avoid the use of Bessel functions, and also to try to solve the problem also for also in the weakly degenerate case where theta is between 0 and 1. And another possible extension is to try to solve this kind of inverse problems also on compact graphs, which is now a work in progress also with Alessandro Luca from Nancy. So thank you for your attention.
Okay, thank you very much, Veronica, for this very nice talk. Let's ask the audience if there are any questions or comments. I think, as usual, you have a microphone to use, and also you can use the chat. So please go ahead.
Hi, can I ask a question?
Yes, sure.
Yes. Hi, Veronica. Thank you very much for your presentation. I think that it seems to be a broad work and very extensive, no, with many different kind of inverse problems, and also the extension to higher dimensions is interesting. And I was curious because something caught my attention. I think that if I am not wrong, in the first inverse problem that you have shown, the observation goes down at some time t star, no?
Okay,
In the first inverse problem that you presented, I think maybe, yes,
yes.
at some time t star. And then later you presented other two inverse problems, problem 1 and problem 2, and in the problem 1, the observation goes down when the initial data was unknown. The observation goes down in a time interval, no?
Yeah.
And it caught my attention. I don't know why, but I don't know if that has an explanation or...
To obtain the uniqueness result, also for the initial data, we need to consider a time interval because and also the analyticity, because we need to consider t which goes to infinity in order to obtain a result. So we need not only a one-point measurement, but a measurement on an interval in order to...
Because you have an extra unknown that is the initial data, no? And maybe, yes. Yes, that's all. Thank you very much for your presentation, Veronica.
Thank you.
Are there other questions? So Luis, Luis Japu. So in the figure, the iteration of a map of a numerical schemes. Luis, can you use the microphone? So he's asking in the figure, the iterations of a map of numerical schemes. I don't know.
Hello?
Yes. Yeah.
Hello?
Luis, yes.
Yes. The iterations, the iterates in the horizontal axis are referred to what in practice?
In this plot, the iteration are the iterations in the computation of the initial datum in the left subinterval 0a and in the right subinterval a1, because we have in this case a piecewise constant initial datum with different constants on the left subinterval and the right subinterval. So we have the iteration in our optimization algorithm.
Yeah.
Okay, optimization algorithm.
Only for the initial data in this plot, but of course also for the other unknown, which is the degeneracy point, but in this plot only for the initial data.
Optimization. Other questions? Just one question, Veronica. Can you explain briefly what are the difficulty for weakly degenerate case when the degenerate power is less than 1? Okay. In the weakly degenerate case, we don't have automatically this condition. We don't have this condition, and this means that we are not in a situation where there is no transmission of information between one side of the degeneracy to the other. So we cannot analyze the spectral properties considering two decoupled subproblems. So we can perform a similar spectral analysis only for some specific configuration of the degeneracy point, in particular symmetric configuration of the degeneracy point. So we are not able to perform all the spectral analysis with Bessel functions in the same way as in the strongly degenerate case. Okay, so thank you very much. We thank you again for accepting the talk, to give a talk in this seminar, and thank you very much. Thank you.